Welcome back to this course in Engineering Dynamics, and this video will be doing a sample problem on the general plane motion of a rigid body. So problem here is taken from the textbook of Hubler. So it's problem F16-7. So the problem is, if a roller A moves to the right with a constant velocity of 3 meters per second, determine the angular velocity of the link and the velocity of roller at the instant theta is equal to 30 degrees. So we have this link over here, and the ends of these links are just rollers, and it's resting on this vertical let's say vertical wall, and then this ground over here. So if roller A moves to the right, so for example this roller moves to the right, so determine the angular velocity and the velocity of roller B. So meaning, if this one moves here, then it's just like this. So if it moves here to the right, then the point B has to move downward. So the question is, what's the velocity here? And then if you notice, if it rotates this way, then meaning that the angular velocity is counterclockwise. Okay, so we have to find this velocity and then the angular velocity here. So in solving, since we will do this using the relative velocity analysis, then let's label the coordinate systems here. So let's say, since point A we know the velocity here, so this is the reference point. So I'll label it in this manner. Okay, so now we have to apply the relative motion equation, which is the velocity of B. So let's do it in terms of vector notation. So velocity of B is equal to velocity of A plus the relative velocity of B with respect to A. So this one, this is just the cross product of the angular velocity and the position vector. Alright, so now let's substitute the value. So we have a velocity of A, which is equal to 3 meters per second. So notice that this direction is along the x direction, so meaning we only have 3I. So we're doing a vector notation here, and for this cross product, then we get matrix. So recall that for a cross product we have the ijk component, and then the second row is the angular velocity. So here for the angular velocity, it's actually this way. So if we try to draw it in three-dimensional, so for example, this is our x, this is our y, and then this is our z axis. So notice that even though we draw it in terms of a rotational symbol, what it actually means is, alright, so for example, let me draw it here. So let's say we have the xy plane, and we're drawing this rotational symbol along this xy plane. But actually, what it means is it is a vector, and that vector is actually just pointing towards this z-axis. Okay, so if the rotation is counterclockwise, then the vector is actually along the z-axis. So recall that the cross product, a vector multiplied to another vector in a cross product fashion, what we get is another vector, but that vector is out of plane. So recall that, for example, we have this this is our x, y, sorry, z. So these are plane, and what we did before is we multiplied vectors here. Let's say vector a and then another vector b, and when we find the cross product of that vector, what we actually get is another vector, but it's actually pointing out of plane. So how do we know if it's pointing along the positive z-axis or the negative z-axis? We use the right hand rule. Right, so specifically, if we try, for example, this is our plane, and let's say this is x, this is y, and the z-axis is pointing going out of plane here. So it just means that if our rotation is counterclockwise, meaning we put our right hand here, and see the rotation goes along this the rotation is along this plane, but then the axis of rotation is the direction of your thumb finger. So if it is counterclockwise, then you are along the positive z-axis. But if that is counterclockwise, then meaning that you are your vector is actually pointing along the negative z-axis. All right, so I hope that clarifies some confusion over the vectors here. So since this is a vector, then it just says that along the x direction, it doesn't have any component, and as well as with y, but for the z the direction it has. So meaning this is there's some magnitude here, but actually that magnitude is unknown because that's what we are actually finding. So let's just put a symbol omega. So for this case, let's, even though we don't need we don't need to put the symbol or the subscript AB because it's just only one bar here, and just take note that this rotation here, actually this is the rotation of the link itself. All right, so moving on. So since this is a cross product of the angular velocity and then the position vector, to take note, this position vector is the position of B relative to A. So what is this position of B relative to A? So that is actually the reason why I put this coordinate system, because it's just the same thing when you draw in the CAD programs. We do a lot of changing these UCS. So here, from this point going to that point along the x-axis, we're actually going to the left. So meaning we have a negative value here, but since we have this angle given and then this hypotenuse, then actually we can solve for the x component and then the y component of the distance. So here, if we solve then it's just 1.5 cosine 30, so that's 1.3. And then the other one, 1.5 sine 30, so 0.75. Okay, so along the x we have negative 1.3. It's because it's to the left of point A. Then along the y it's 0.75, and along z it's just 0. Okay, so we move on. So we have 3i plus, recall that when you solve this one, for example, there should be ijk. So if you're solving for I, the shortcut method is you just have to cover this one, this I column, and then you do 0 times 0 minus this one. So it's just like, okay, so 0 times 0 is just 0, so minus 0.75 w. That's along the I direction. And then along the j, you just cover this one also, and what you get is, and take note by the way that for j direction it's the negative, so 0 times 0 minus negative 1.3 minus negative 1.3 omega. So that's along the j direction. All right, so that's okay. Let me check. So 0 0 minus, oh, sorry, so if it's minus negative, then this one should be positive. Okay, and then along the k direction is just 0, because 0 when you go downward minus 0, so it's just 0 here. Okay, so therefore if we try to simplify, what we get is 3i minus 0.75 omega I minus 1.3 omega j. Okay, so since we have two unknowns, we have this unknown, the angular velocity, and then the velocity of p, then we will need another equation. So this one is the first equation we have, but for another equation we can solve it here. So we notice that the v sub b we have is also a vector. It's also a vector, but in terms of vector components, we can write it as v sub b is equal to negative vb along the j direction, because it's downward, so it's negative vb. So this is the magnitude, and then this is the unit vector. So now we have two equations, two unknowns, then we can solve already. So equating the two equations, all right, so I think we solve, okay, equation 2. So here, let's equate. Okay, so 3 sub I minus 0.725 omega I minus 1.3 omega j is just equal to this one, the negative vb Okay, so we have a vector on the left side and then another vector on the right hand side. So what we do here is actually it's like the same method that we also do in the differential equations. I think it's on the topic of partial fractions. So we're just equating the left hand side and then the right hand side. So here we try to look at the i's, and we'll just neglect first the j directions. So we'll just look at the I. So what are the terms that has i's? I components here on the left hand side. We have 3 minus 0.725 omega. Okay, and then we equate that on the right hand side. So on the right hand side, we look for i's. So we only have j here, so meaning that this one is just 0. So that's our equation 1. And then our equation 2 would be the j's on the left hand side. We have negative 1.3j. Oops, sorry, no need to write the unit factor. So 1.3 omega is equal to negative VB. So this is our equation. So we can label that equation 3, and then this one is equation 4. Okay, so from this equation we can actually solve for this. So is equal to, we put this 3 on the right hand side, so it's just negative 3 divided by negative 0.75. So 3 divided by 75, it's just 4. So omega is just 4 radians per second. And then for this equation number 4, since we now already have this angular velocity, then we can solve for that. So since negative, then negative and negative cancels out. So 1.3 times omega times 1.3. So times 1.3, then 5.2 meters per second. Alright. Okay, so to review on what we did. So here's our problem. There are rollers on both ends of the links. We have A and B. And if this point A goes to the right, then what will happen to point B? So it will go downward. So it will have a velocity, and we label that vis-a-vis. And because it goes downward, and then this one towards the right, then there's actually a rotation going on. So the problem asks us to determine this angular velocity, and then this velocity of point B over here. So first, what we did is we used the main equation that we have for the relative motion, which is just vis-a-vis is equal to vis-a-vis A plus the relative velocity of B with respect to A. So in our analysis, I transferred this UCS into point A because that's our reference point. So this omega and then this position vector, position of B with respect to A, this is a cross product, and we use this matrix maths here. Then we do the maths, and then we get an equation, and we label this as equation 1. And then since we have two unknowns, so we're gonna need two equations. So another equation is the expression of the velocity of B alone. So here it's going downward, so along the y direction, so we have negative VB J. And then we equate those two equations, we get this one, we get these expressions, and we can actually something like separate the i's and then the j's. So if we separate the I, we get this one, we get the angular velocity. And then if we separate the j, we can solve for the velocity of B. And at this point we already have this value of the of the relative velocity. So therefore we can solve for this one. So that's the answer. Alright, so in the next video we'll be doing another sample problem for this general plane motion of rigid bodies. See you in the next video.